In this lesson, we'll apply classification algorithm in security price prediction using R programming. We'll revisit the ABC price case study. First, we'll train linear logit and probit models using our training dataset. We'll evaluate various statistical goodness of fit measures and visualize the performance of these algorithms. These measures include classification and confusion metrics and ROC curve and area under the curve. We'll also train a simple algorithmic model to find the best performing algorithm using a simple performance object, which is the simple average of model classification, accuracy, sensitivity, and specificity measures. In this video, we'll recap the ABC stock price forecasting case study, and then we'll see the application of classification algorithm in the context of security price prediction. Recall our discussion about ABC security price prediction case study in the context of regression algorithm in a series of videos. We noted that stock price prediction or stock return prediction is an attempt to determine the future value of a company based on the analysis of factors which impact its price movement. We noted that there are a number of factors that help in predicting stock prices. These can be macroeconomic factors like the state of the country's economy, growth rate, inflation, among others. There are also various factors that are more specific to a stock like profit margin, debt equity issues, sales of a company, and so on. In this particular case, we are given the data for a stock market price of ABC company, its returns, along with the Nifty and Sensex returns. So we have Nifty, Sensex, and Nifty returns, along with the dividend announcement and sentiment. Sentiment variable is provided. Sentiment essentially reflects investors' view about a market. It can be positive or negative as well. And then dividend announced. For example, when dividend is announced here, the value 1 reflects that on this particular date, the dividend was announced. Now consider a portfolio manager who has built a model for a particular stock. The manager wants to predict whether in the next period the stock price returns will go up or down. That means whether it will be positive, return will be positive or negative. Data starts from 2007 and goes on till 2019. So we have approximately 13 years of data, and we have daily returns for ABC, which is basically the change in price here in this column. Along with that, we have variables, market index variables like Nifty, Sensex, sentiment, and dividend announced as we discussed. Please note that these Sensex and Nifty are two major stock market indices in India. They are benchmark stock market indices that represent the weighted average of largest Indian companies. Sensex represents average 30 largest companies that are most actively traded, and similarly Nifty represents a weighted average of 50 largest Indian companies. To summarize this video, we will perform the following task using R programming. First, we'll create a dummy variable which is 1 when stock prices go up and 0 when stock prices go down. And then we'll segregate the data into training and test data sets, similarly as we did in the regression model. Then we'll train and build the model using simple logit probit classification algorithms, using market index as the independent variable and up and down dummy variable. So remember, the up and down, the positive and negative returns will be represented through a dummy variable, like we said. So 1 when there is a positive return, 0 when there is a negative return. So this will act as a dependent variable, while market returns like Sensex or Nifty will be employed as an independent variable. Next, we'll evaluate in-sample performance and out-of-sample performance of these models. We'll compute the marginal effects of the independent variable, visualize the performance of these models using ROC curve, and then examine the classification accuracy of the model and compare it with a similar linear probability model. In this video, we'll start with our implementation of classification algorithm with ABC security price study. So we'll talk about ABC security price prediction using classification algorithm. So we'll conduct the following exercises. First, we'll set the working directory, we'll load the relevant packages, and then we'll read the data, and then we'll create the up-down variable, which is 1 when returns are positive and 0 when returns are negative. So first, we'll set the working directory here using this session tab, choose directory, and click on it. So notice a setwd command has appeared. So for reference, for future reference, I'll just copy paste this command. So whenever I'm working on this file in future, I know where the working directory has been set. Now we'll import our ABC data from text. I'll import this ABC data. So the file has been read. And we can see that a view file has appeared. Now instead of naming it, you can change the name also. I'll just copy paste this command, the full command. For future reference, I'll use this command. And instead of using ABC, I'll rather use the name. We can change the name here. So I'll choose the name data file. Already there is one read Excel package which has read through this command, library read Excel, but we need some more important libraries. First, Lubridate to handle date time pack operations. Then we need library of moments if we need to do some statistical operation like movements and all, computation of movements and so on. Then library car, we have already seen the application of library car. Another important library that we'll be using is LM test. Library. So these are some of the important library that we are going to use. Some of them already used in the regression modeling. Library tidyverse for any kind of tidy operations. Library of margins for examining the marginal effect of logistic regression coefficients. For ROC, for generating ROC plot, we have ROCR library. We have Caret library for classification matrix and some various important measures. And lastly, there is also one patchwork library which is for some good plotting. So these are some of the libraries that we are going to use in our operations. We have read the data also now. So first we loaded the relevant libraries here. Loaded the relevant libraries, then we read the ABC data. Another very important operation is checking whether your date. Often it is important to check whether date variable in your data is actually in the date format or not. So sometimes the date variable is read as character. Let's see if that is the case. So it is read as in fact it is read as date time. So POSIX-CT represents not only date but time as well. But we are only dealing with the date part of it. So I would, in the interest of clarity, I'll just change the class to date. This is important so that there's no confusion while we are doing some operations. So when I'll run this command, I will convert my date from date time to exactly date. Now if I run back this class command, notice in the console window you have date. It is appearing as date, so that time aspect is. Lastly, I need to convert or rather create up down variable which is 1. So this variable should be 1 when returns are positive and 0 when returns are negative. So a very simple operation is needed to create this variable. Notice now we are working with tidyverse, so it's quite simple. I'll use this assignment operation. Then I start working with this symbol. I start working in data. I request it to create through mutate command. I request it to create a new variable. Its name is up down. This variable is equal to, and I'll use if else operation. If else operation, if, and remember ABC variable contains the returns, so if the returns are greater than 0, then I want it to be 1, and 0 if the returns are negative. Now if I run this command, we would like to check our data, so I'll use the head. Since we are in reverse, I can simply type data, and notice there is a variable up down created. When returns are positive, ABC returns are positive, this variable is 1, and when returns are negative, as here in red, it is 0. To summarize this video, we started with setting the working directory, then we loaded the relevant libraries, then we loaded the data and converted its date variable, which was actually date time, to pure date variable, and then we created a new variable called up down variable, which is 1 when returns are positive and which is 0 when returns are negative. We created this variable because ultimately we are doing classification with the help of limited dependent variable, where this up down is the limited dependent variable, or binary response variable, or discrete, you can say discrete variable. In this video, we'll create our sample of test and training data sets. Training and test data sets. So as a first step, what we'll be doing is we'll be separating only those observations that are after 2007. So we'll first, in our data, we'll create those observations using this filter year of date is greater than 2006. So notice in the console, now only those observations are there where year is greater than 2006, and we'll assign this to our new data. So this will create a new data, assign this data to our same name, and now our year is starts from 2007. So this is first step. Now we'll randomly select 80% of the observations as training data set. Using these 80% observations, we'll train our data, and remaining 20% will be used to test our trained algorithm. So we'll create an index variable. The application of this index variable, it will be quite simple. So using the sample command, we are randomly creating an index variable. So notice this, with the sample command, we are selecting data, number of rows with the number of rows, and here we'll specify that out of these rows, only 80%, that is 0.8 into only 80% of the rows are to be selected in this index data. So the objective of this index, this will act as an index in while we are extracting the observations from our data variable. Notice how we do it. So we use train na.omit. So we want to, so first we'll also, sometimes there are missing observations. The best way to deal with them is use this na.omit command, so all the missing observations are removed, and so we save some unavoidable problems. Now we'll simply select only those observations and see how we use this index variable to extract only those rows. So index will act as an index while extracting those rows, all the columns. Notice on the right side of the comma there is nothing. That means we want to select all the variables. If you wanted to select some specific variables like variables 1 to 3, then we would have used this, but we want to use all the variables, so I'm simply using index comma, and now the train variable will contain all the rows randomly selected, 80% of the rows, and please remember these are randomly selected. Now in the test data, again we want to use only those rows that were not used earlier. So very intuitive and interesting use of this minus sign, which tells us that only those rows that are excluded in the, that are not there in the index variable, those rows are to be selected, and again the same comma operation, and we get that in test data. So we have our test data and train data ready. Now as a practice, we'll just have a look at these data that we created. So see that they are not properly ordered. train data and test data, they are not properly ordered. So the next thing we'll do, we'll try to order them with time. So what we'll do is, notice this command train, and I want to arrange this with date. So I'll use the date command to arrange the train data, and now you notice that now train command is with the order of time, order with time. Similarly, we would like to order our test data also. So with this, I'll order the test data with time. Date, basically our date variable indicates the date, so we'll arrange this as well with date. So now that we have created our test and data, train data, which are arranged with time. As a good check, it is important to see whether the distribution of our dichotomous or binary variable, which is up-down variable, has same proportion. What do I mean by proportion? Let's look at. So I want to know what is the proportion of ones and zeros in this up-down variable in our original data. So I'll use this prop.table command, and then I'll put it in tab with table. I'll put in table form. I have the original data, which is data $updown, and I'll multiply it with 100 to get the number in percentage form. So notice it's around 50-50%, approximately 50-50 in the main data set. So I want to see whether this remains the same in our test data also. So I'll use this. First I'll check with the train data, and let's see, very close, it's almost 50-50. And they should not come as surprise for us, because we randomly selected, our sample was very randomly selected, there's no systematic bias. So ideally it should, the proportion of up and down variable, ones and zeros, should be same as the parent data, and it's supposed to be indeed the case, although in test data there's slight deviation, but it is same, so it's okay. So broadly it's not skewed, so ones and zeros are not skewed in any of our samples, test and train. To summarize this video, first we filtered the observations that are after 2006. We wanted more fresh observations, so we started our experiment with 2007. Then we removed any NA observation, not available observations or missing observations. Then we randomly selected 80% of the observations as part of our training data set, and remaining 20% were assigned to the test data set. Finally, we also tested whether the proportions of ones and zeros is skewed in any of these data sets, that is the parent data, the training data and test data, and we found that broadly the distributions of ones and zeros is fairly similar, close to 50-50, although it's slightly different in the test data set, which is 45-54, but still it is okay for our experiment. In this video, we'll train a linear regression model using the training data set, and then compute the classification confusion matrix and performance measures like accuracy, specificity and sensitivity, and see the model performance. We'll evaluate the model performance. So in this video, we'll do the linear probability modeling and performance evaluation. So first, as a first step, I'll assign it to a linear object. I'll create a linear object where I'll assign the train model. Remember that we use lm command for train model. Then up down is the variable, relevant variable, dependent binary variable, ones and zeros. Then we have sensex as market index, and the data that we are using is the train data. Now this trained algorithm is assigned to our linear object. If you want to see the summary of this object, you can simply type the summary command and linear, and notice that this is able to explain approximately 20.35% of the model. The adjusted R-square is approximately 20.35. So we are able to explain that percentage, and also notice the coefficient, which is 12.34. That means 1% increase in market variable leads to an increase in probability of approximately 12% in return being positive. And similarly, we can interpret in a vice versa manner that 1% decrease in market variable leads to 12% probability in a negative or zero, observing a zero, that means negative return. So 12% increase in a probability of negative return. Now we cannot simply model like this. We need to assign or classify these results into ones and zeros, because we only observe what we call probabilities. We do not observe these probabilities. We observe ones and zeros. We always observe ones and zeros. So we need to convert these probability results into ones and zeros, and a very simple way to do that is through this if else. We'll extract the fitted values. So these are our fitted values. Inside the linear object we have our fitted values, and those fitted values, let's say we start with the threshold value of 0.4. We'll use three threshold values, 0.4, 0.6 and 0.8. So if it is greater than 0.4, we'll assign a value of 1, and if the probability threshold is less than 0.4, then we'll assign a value of 0. So the fitted results are put here in the fitted result object. In the next step, we'll compute the classification, or what we call confusion matrix. It's very simple. Confusion matrix, which is facilitated by the caret package that we installed earlier. And here we need to provide our fitted result in the factor form. So using as.factor, we'll create these results in the form of factors. So there we have our fitted results. And then we'll also provide our actual data. So then we have actual data as dot factor actual data. So we have our actual data. So this is our actual data, and we'll put our computed results. We'll put our computed results in the object named as CM. So the CM will carry our fitted objects. Now I want to compute my performance measures, accuracy, sensitivity and so on. So I'll create this performance underscore 4, this performance object, and this will carry, I'll assign in the table format. I'll create a sort of table threshold. So threshold value of 0.4 and accuracy. Now please note, for accuracy we'll assign a name of accuracy, but I need to extract this from the accuracy. How do I do it? I type it accuracy like this, and then I also need to extract the sensitivity. So I put a name of sensitivity. I assign, again I use that CM object, CM dollar by class, and I put a name of sensitivity. And lastly, I also want to extract specificity, and for that again I'll use this CM dollar by class, and I'll put the argument specificity. So here I will get my performance object, and notice I can print the performance object very nicely. It has, for a given value 0.4, whatever the accuracy, sensitivity and specificity that are computed. Now I need not write the code again. I want to compute it for a threshold value of 0.6. I can simply create another object, performance underscore 6, and I'll use a value of 0.6. I'll run this, and all the results are stored. Later we'll examine the results. First we'll create for 0.8 also. So I'll create the performance object for 0.8. This is we are doing for linear probability models, LPM. So we are creating the objects. Next we'll create 0.8 for 0.8 also. Very simple. We'll create it for 0.8 also now. Lastly, we'll combine all these objects for our future purposes. We'll combine this linear underscore performance object, and we'll type it as rbind. There are three objects that we need to combine: performance 4, performance 6 and performance 8. Now I have done that, but I will also add another command where I would like to add a class column. We are doing it because in future when we are comparing it with logit probit models, I'll make use of this new variable class, and we'll see the use shortly. We'll understand why I'm adding this, but for now I'll just print this object linear performance, and you notice we have threshold levels, accuracy levels and sensitivity levels. Okay, so I also need, by mistake I forgot one step I needed to add, so I'll just add this step here. I simply needed to compute. Every time I do that I need to compute again as well. I forgot that, so I will add 0.6 here, and similarly I'll again add here 0.8 here. So I just rerun the commands again so that it's done properly. So my model is already there. I simply need to run this, And once I run this, now we have all the threshold values, their accuracies and sensitivities and specificity. To summarize this video, we trained a linear probability model using the trained data set, and then using these fitted results, we converted them into ones and zeros with our threshold values of 0.4, 0.6 and 0.8. Then we computed the confusion matrix, and subsequently we computed the important measures of performance, which is accuracy, sensitivity, specificity, and then we stored these in our linear performance object for future use. In this video, we'll train our logit and probit algorithms using the trained data set, and then we'll compute some performance evaluation measures such as pseudo R-square. We'll also see their marginal effects, and then we'll compute their performance, evaluate their performance using threshold values of 0.4, 0.6, 0.8 by using measures of accuracy, specificity and sensitivity. So we'll first train our logit performance object. Now this is quite simple. We'll use this, we'll assign the trained object into logit object, and we need to simply use GLM, generalized linear models, for GLM, short for generalized linear models. Now I'll not write the formula again, I'll simply use the same formula that I used in our linear object. Remember, the formula was dependent variable was up down and independent variable was market variable. Now again, our data set remains the same, the trained data set. Only we need to specify the family of models that we want to use, and this is the binomial family of models, which is logit. So our trained object is assigned inside the logit variable. Remember the concept of pseudo R-square, where we wanted to create another restricted or null model, sort of null model, where we are not using any variable. It's a constrained model, so the dependent, there's no variable, we are using simply putting 1 to reflect that there's no variable, only constant term. It will be again trained with trained data set. Its only purpose is to check the pseudo R-square. Remember the discussion on pseudo R-square in the video topic goodness of fit measures in lesson 1. So family binomial, again binomial and logit. So this null object, restricted object where there are no variables, it will help us in creating our pseudo R-square measure. Now the pseudo R-square measure is simply, remember the formula, 1 minus log likelihood, I'll select the log likelihood. So on numerator we have log likelihood of our logit object, and it is divided by our log likelihood of null, which is restricted model. Let's see what value we have. So in the pseudo R-square we are able to, now please note this value, we have 11% of pseudo R-square, but please remember, on a standalone absolute basis we cannot interpret much. It is more of a relative concept, so we need to have a competing classification model, logit or probit competing model, which can help us compare. We can compare with that, but on absolute standalone basis this is not exactly that intuitive as compared to R-square or just R-square measures. Also we have margins package we installed earlier, where we can check the marginal effect of the coefficient. So we had the market coefficient Sensex, and it seems that its impact is 15.75%. That means if market increases by 1%, on average a positive return, the probability of a positive return increases by 15.75%, and vice versa. If market decreases or market goes down by 1%, then probability of negative return increases by 15.75%. Now please remember, in order to fit our results, we need not write the whole code again. What we'll do is we'll simply copy paste the codes that we wrote for the linear model. It's quite intuitive and simple. We'll just simply copy paste these codes and see how it is done with R. It's quite intuitive. I'll simply copy paste these codes. Very minor modifications are needed, so we need not write the full codes again. Just have a look at this. So here I'm using linear instead of linear. I'll just simply use the logit. I'll replace it with logit. So that is first change. So I have put it as logit, and the second change that I want to do is Similarly, in the 0.8, I will again here change as well logit. And lastly, the third fitted results, where we are converting the probabilities. Here we are basically converting the probabilities into ones and zeros like we did for the linear model. Now I'll just change the name of these performance objects to logit performance. So, and then lastly, this logit performance. And again, as we did earlier, we'll change this name from linear to logit, and we'll just run these commands to assign these values. So it's quite easy, right? We didn't have to write the entire code again. We simply copy pasted, and that is how it works in R. So we simply copy pasted the values, and we have our measures of sensitivity, specificity ready for us. Now again, now we want to compute it for probit, and we want to compute the performance evaluation of probit. So we'll do that. So at this stage, I will not do many changes. I'll simply replace the logit with probit. So I'll simply just copy paste the entire thing, and the only thing I had to do is to replace logit with probit. So I'll simply replace wherever I have written logit, I'll just simply replace it with probit. So I'll just type probit here, probit. 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 I'll just simply replace this logit object with probit object. I'll just replace all the places where I've written logit. I can just copy paste probit. Everywhere where we have written logit, we can write probit. So everywhere we have written logit, we are simply writing probit. And with this, we are done. So we'll start with the implement. This one is left, so I'll just type. Okay, so now we'll start with training our probit model. It's quite simple. I'll just run this command. So we'll run the probit, we'll train the probit model, and then we'll also run this null command to get that restricted model as we did earlier. We'll compute the pseudo R square. Pseudo R square is also there. It's around similar, around 10.5%. More importantly, we look at the marginal effects of the probit model, which is 14.56. Now the coefficient has similar value as we had for logit, and the interpretation goes like this. If there is a 1% increase in market, then the probability of a positive return increases by 14.56%, and vice versa. That is, if market goes down, then probability of a negative return increases by 14.56%. Now we'll run the remaining commands to store our fitted results in the objects. As we did earlier for the logit model, we'll do it for the probit model also as well. Interesting to note, if I compute the correlation between the fitted logit dollar fitted values and probit dollar fitted values, the correlation is very high. That means almost 99%. This is intuitive as well, because we were expecting this result. The distribution of ones and zeros is very similar across the objects, almost 50%. In such scenarios, it is expected that logit and probit will give similar results, and therefore we also expect that the performance in terms of various measures is going to be similar for logit and probit approaches. To summarize this video, we trained our logit and probit model objects through logit and probit algorithms. We evaluated their performance with pseudo R square measure, and also we examined the marginal effects of the market coefficient. Subsequently, we evaluated their performance on measures of accuracy and sensitivity, and specificity using confusion or classification metrics at threshold values of 0.4, 0.6 and 0.8. Now that we have computed our performance objects, in the next set of video, we'll compare their performance. In this video, we'll evaluate the performance of logit, probit and linear objects algorithms by computing the correlation between them and also through visualization. So we'll first compute the performance by computing the correlation, and for that let's create the correlation object. Correlation is simply cbind. Correlation object is simply cbind. We'll compute the data frame, which will include the linear fitted object, logit fitted object, and also the probit fitted object. So we have saved our fitted values inside this core underscore ob, and now we'll compute the correlation matrix for this, which is very simple in our core underscore ob. Let's see the control in the console window. Let's see the printed correlations. We can see the correlations are very high. In fact, 99.9, which we already saw in the previous video, between probit and logit fitted values. For linear values also it's very high, on almost 95%. So this is expected. Generally this kind of high correlation expected when the distribution is very symmetric. We have 50-50% ones and zeros for our training data set, so such high correlation is expected. But still we need to compare whether which one of these models, linear, logit and probit, is performing well, which we'll do shortly. For that we need our measures of accuracy, specificity and sensitivity. So we'll first, as a starting point, we'll first combine all the performance objects in our performance object. We'll combine all of them by creating a table kind of data frame, which is easy to process. We'll combine all the three performance objects. That is, first is our linear. Remember, in the previous video we computed the linear performance object, logit performance object, and we also computed the probit performance object. Now that we have combined, we can see what is there inside this performance object. So all the variables, threshold, accuracy, sensitivity, along with their class. Now here the class variable will be important when we'll be doing the plotting exercise. So we'll try to visualize them. For visualization, so we'll visualize them. Now for visualizing, we'll make use of ggplot command. It's very interesting. So first we'll create the p1 plot, ggplot, and here we'll have the performance object. For ggplot we need to provide the aesthetics. So what exactly we want? We want threshold levels. Now threshold levels can be in the numeric form also, but we'll make use in the factor form, that is category variable. So threshold object, and then we also want to plot accuracy, but for accuracy we'll use the numerical properties, accuracy. So this is our accuracy. Then we would like to print, because these are simply points, so we'll like to make use of geom point while plotting them. So geom point will ensure that we have a plot of, and now here notice, now in this aesthetics we are providing color to be segregated as per the class, and that is why class variable that we added is important, because this will help us segregate the plots in terms of their different classes. So this is first object. In fact, we can print it right now, and we can see that p1 object, you can see that accuracy is printed. 3 objects, notice the accuracy, while we can examine them later on, but just to give us a flavor, you can see how they are plotted, but we'll compare them later on. Then similarly, like p1, I can also plot p2. I have p2 object, I can create the graph object p2, where instead of accuracy I can use the variable sensitivity. I can simply just copy this sensitivity variable here. So this is my sensitivity. I'll store this in p2, and the last one is the specificity, p3 specificity. So here I'll use the specificity object. So here p3 I'll use the specificity object. I'll just copy it. One more thing, I need to adjust for the x and y axis, so I need to add those x, y axis lab commands. So for example, I need to have, let's say, X lab. In my accuracy object, I'll have the x-axis always remains the threshold, and y-axis here, y-axis, let me use next line for this, so that will be better, make it more clear. So y-axis I'm using as since accuracy, because this is P1 is for accuracy, so I'll use accuracy here. I'll just copy paste this, I'll just copy paste this and make use of. In the next P2 we have sensitivity, so instead of accuracy I'll replace it with sensitivity. Similarly for P3 I have specificity, so I'll add specificity. Now I have all the three plots. I'll again just run these commands to ensure that we have proper P1, P2, P3. Now it's time to plot them, and very intuitive, very nice, because we had one patchwork library, if you remember, we added, which will help us plotting these objects like this: P1, P2, P3. They'll be very nicely plotted, and notice they are there very nicely lined in rows. And now we can compare their performance. So just notice the logit object, which is the green window, is always, most of the times, it is higher on the higher side, while the values are very close to each other, which we also saw in terms of the correlation number. The correlation was very high in the fitted values. Nonetheless, the green one, the logit, seems to be doing better most of the times. The green one, especially on the accuracy level, it is particularly high. Sometimes there is change in the sequence, but still most of the time the values of the logit for accuracy and sensitivity is reasonably high, except a few scenarios. For example, here the linear one is doing well in terms of sensitivity of 0.6 and so on, but mostly it seems the logit model is doing well. To summarize this video, we computed the correlation across all the three linear logit and probit models, fitted values. Then we plotted them for the three threshold values of 0.4, 0.6, 0.8. We noted that while the performance on all these measures are very close for all of them, nonetheless, logit model seems to be doing marginally better than the other fit models. We were expecting this close performance, this close column performance, because the correlation across all the three linear logit and probit fitted values seems to be very close to each other.